we have this same equation that I just derived. Once again, delta G total, right, equals the standard free energy of the reaction plus RT natural log of Q. And we remember that when we're dealing with initial conditions, we don't use K, rather we use Q, okay? So now something special happens when delta G equals 0. So I talked about that previously right here, right? This is often where something interesting happens. So what ends up happening now when this delta G total is equal to 0, this special relationship emerges, and now instead of having Q, I have my equilibrium, okay? So when delta G total equals 0, we have achieved equilibrium, which is pretty cool. So if we think of this graph, right? So we can imagine for the total process, let's say, okay, if we looked at delta G total, then, this would be my initial delta G, and this would be my final delta G. So we can see that would be a negative delta G, which would tell me something's happening spontaneously, but I don't have any equilibrium right here because I don't have any place where now my total delta G is equal to 0. But instead, if I had a feature that looked like this, right? Now, at this point C right here, okay, that now corresponds to delta G total equaling 0. And so now when I look at what's going to happen in my final and initial condition, we know if I'm starting here initially, I'm going to end up right here on the final condition. And that is going to be described by equilibrium. And we also know, right, kind of based on this figure, that I could reverse that if I wanted to. So if I started over here with too much product, then we know that my reaction is going to have to shift to the left. All the same, it's still going to end up at that equilibrium point, which is kind of cool, okay? So now continuing along. So once again, if we were looking at this simple equilibrium reaction, let's say equilibrium between A and B. So very simple reaction, all right? And here now I put fraction of A reacted on the x-axis, okay? So if you look at the way this is going here, we're seeing that now we get this minimum occurring right here, right? And you notice that that's also occurring at, let's say, a mole fraction of A, which is greater than 0.5. So this reaction would actually tell us that K is greater than 1 because my equilibrium position right here is occurring with the majority of A reacting, okay? So for example, right, if this equilibrium was right at the 1.0, there would be no equilibrium at all. It would just be a complete reaction. Or if, let's say, my equilibrium occurred somewhere right here, right, that would tell me K is less than 1, so reactants are preferred. And so that's what we can say, right? What does it mean to be on the left or the right, okay? Well, in this scenario, equilibrium lies closer to products. So this would be a K greater than 1, which means we're on the right. This, on the other hand, would be a K less than 1 because the equilibrium position lies closer to reactants, all right? So we can see here for the perfect scenario of K equaling exactly 1, that will correspond to now a free energy of reaction. So that's important to note that this is now talking about the reaction. That would give me a free energy of reaction of exactly 0. This is a super ideal situation, which is just not very likely, okay? Ideal, not likely, right? We've never had a scenario where we see an equilibrium constant being exactly equal to 1. What we see instead is typically K greater than 1 or K less than 1, okay? And as we might guess, a K greater than 1 means a free energy of reaction that's less than 0. So it's a spontaneous reaction, okay? So we'll say spontaneous. But a delta G of reaction that's greater than 0 is going to give us a K less than 1, and that's going to be non-spontaneous. And I work that out via the following. So we have this equation right here. Oops, let me keep going back, sorry. So 0 equals delta G plus RT ln K. So if I rearrange this equation right here, then I end up with this equation right here. Okay, so all I did was add it over to the other side. And now, right, if K is equal to 1, then the natural log of 1 is 0. So that would give me free energy of reaction of 0, which is not very likely. On the other hand, if I have a K that's greater than 1, when I have a natural log of a number greater than 1, it's a positive number times a negative, gives me a negative delta G. So it's spontaneous. It'll spontaneously proceed towards products. But now, if I have a K less than 1, we recognize the natural log of K less than 1 is a negative number. A negative times a negative gives me a positive. That's a positive free energy of reaction, which would be non-spontaneous. Okay? And there's another way I can rearrange this equation for calculations, and I'll show you that momentarily.